Good afternoon, everyone. Hope you had a great meal, great lunch. Crowded room. Can you hear me in the back? Right. All right. Great. So, welcome to this session. We'll talk about self-healing applications, which is like the holy grail of every ops member. All right. Just have applications that just fix themselves. You don't have to SSH to production from your parents' Wi-Fi on Friday night. It just fixes itself. Who here has ever SSH to production from his parents' Wi-Fi? Raise your hands. That's right. All right. So it happens, okay? Because stuff breaks, and usually stuff breaks when we introduce changes. But changes are a natural part of the application lifecycle, and it's natural. We want change because we want to introduce new features, and we want to fix bugs, and we want to patch releases and stuff like that. But changes cause breaks. So how can we manage those breaks, or even better, how can the system just fix itself? So that's our topic for this session. Oh, it is a crowded room. And we'll show you how to do it using Docker and Kubernetes. Now, Docker and Kubernetes are pretty new technologies in the market. We're talking about 3-4 years, something like that. So best practices and new methodologies are emerging. They're just forming now because we're not just now trying to get experience with those tools and platforms. But there are common features and common things we can do with these things that can better help us, the people in charge of making the stuff run in production, to actually manage this. All right, so about me, I'm the DevOps team lead at Nuvo Group. Nuvo Group manufactures, actually designs, manufactures, builds, produces, ships, whatever, pregnancy monitoring device, which collect data from pregnancy and process them in the cloud. And we have a pretty big environment on AWS. I'm also a certified solution architect at AWS. I do a lot of container and orchestration jobs. I used to be a consultant in my wild days. So I did a lot of training and lecturing, and here I am. So that's me. All right. So what are we going to talk about in this session? First of all, we're going to try and talk a bit about the challenges of running production system, and more than just a production system, but a distributed production system, which goes pretty nicely with Docker and the containers and the whole microservice movement we're experiencing lately, because it is a distributed system. The more moving parts you have inside your system, and think of the system as a whole, more servers, more containers, more stuff to look into, there's a big challenge on how to run the whole thing together so it doesn't fall apart. We'll talk about the Kubernetes project himself. Those of you who have no experience with Kubernetes or haven't heard too much about it, it's a big buzzword going on right now. Look at the room. Okay, I think this is the biggest session ever. So we'll try to demystify a bit the Kubernetes project, talk about a little about the history, the goals, the approach to orchestration, what is orchestration. We'll look a bit about the Kubernetes architecture, because it's important for our final point in this talk, which is actually what we're here to do, is how to manage an application's health. But before we can talk about how to manage that health, we need some background understanding how Kubernetes enables us to do that. Okay? So the challenge. Well, that's the challenge, basically. I mean, running a container on your personal laptops, that's like the easiest thing ever. You just Docker run. Once you have your Docker file, you got your container. This is like the easiest thing ever. It's like really easy, really stupid easy, right? But the challenge is moving from a single container running on my laptop to hundreds or thousands of containers running in a cloud environment when I don't have direct access to the container itself, where I need to now figure out where to place my containers, where to schedule them, how do they even communicate with one another, how do they even find one another. So it's like moving from a mouse size to an elephant size. And if we want to break the challenge to concrete, stuff, we can see a bunch of things that we need to take care of when we actually move to production. You got things like, how do we scale? Scale vertically, add more resources to a component, or add horizontally, add more replicas. You got things like how we do discovery, how we do security, how we do load balancing, how do we persist data. It's like a bunch of concerns we have to keep track of when moving from that single cute tiny container running on my laptop to thousands running on some cloud environment. Now, we're not going to talk about all of these issues, obviously. We're going to talk just about this tiny, tiny thing called health and readiness checks. Now, all of these challenges, actually all these points listed on the screen, actually have solutions, or Kubernetes actually provides solutions on how to handle all these challenges. Solutions could be like creating a cluster, which is a logical unit of resources, using config maps to share configurations, using probes for readiness and liveness, DNS, etcd, secrets, container networking, and a lot of other stuff that Kubernetes provides, not because someone was bored, but because these are real-life challenges that need to be addressed. We can't just ignore it and say, okay, I'll do some voodoo and have my tokens some magically appear inside my application. This is a real concern we need to look into. So we'll discuss the health and readiness checks, and we'll look at it in the context of how to manage the application's health. All right, so that's the challenge. Let's talk about the Kubernetes project himself. Kubernetes was announced by Google in mid-2014, and it was hosted on GitHub basically as an open source from the very beginning. And it's written in Go. Version 1, the stable, first version stable, is July 2015. Now, the interesting thing about Kubernetes is it's not a Google project. It never was a Google project, meaning pretty early stages when they uploaded it to GitHub and open sourced it, they donated it to the CNCF, the Cloud Native Compute Foundation, which is actually a foundation dedicated for a lot of open source tools that are cloud native by design. And you can find projects like Kubernetes himself, you can find projects like Prometheus, like Fluentd, a log harvester, and all other kinds of projects which are, cloud native. They are built to run on clouds, they are built to support distributed systems. All right, so Kubernetes is the orchestrator, the scheduler. Other tools like Prometheus provide metrics and monitoring. Fluentd provide logging, and other such stuff. All right, Kubernetes himself comes from a Greek word for helmsman or pilot. All right, one that pilots the ship. And it was heavily influenced by Borg. Right, Borg is the internal tool Google uses to manage its containers. So a lot of ideas and concepts that introduced into Kubernetes actually originated in Borg itself. All right, so that was the history. Presently, Kubernetes is currently at version 1.9. 1.10 is a beta. Kubernetes itself is the GitHub repo is a hub for a lot of sub-projects all related to Kubernetes himself. There's the orchestrator, the scheduler, Kubernetes, Kops, Helm, Hipster, many other projects. Supported on multiple environments. You can run Kubernetes on bare metal. You can run it on the cloud and a hybrid. Being a cloud native framework by design, you get the most benefit when you run it on a cloud provider, but you can just the same do it when you're running on a bare metal. You can roll your own, just download the source code, compile it, install it, have fun, or you can just use it as a managed service from a cloud provider. Most major cloud providers today allow provide a managed Kubernetes service, Azure, Google Cloud naturally, and AWS just announced one in reInvent last year. Major players or major companies you might have heard of using Kubernetes, eBay, GitHub, Pearson, Box, SAP, a lot of big companies, enterprise companies, not just like local startups using it. All right, how does Kubernetes even approach the idea of orchestration? All right. So these are like some common, top level ideas and concepts that Kubernetes uses. The first one is, of course, declarative, not imperative, which means don't tell me how to do things. Tell me what you want to do. I know how to do these things, but I just need you to tell me what to do. And this really goes hand to hand with the second sentence now written down there. It's the idea of a reconciliation loop, all right? And we'll look more deeply into the idea of a reconciliation loop. But the concept is, once you have a declarative state, give me 3 of these, all right? We just want to reconcile reality with the desired state, okay? We'll look into it in a bit. Kubernetes itself is made of loosely coupled, extensible, stateless components mostly. There's just one central state store inside the cluster. For the Kubernetes mine of the application workloads, which makes it very, extensible. You don't like the API server, drop it, roll your own. You don't like the scheduler, all right, drop that and roll your own. One of the major things Kubernetes promotes is infrastructure as code paradigm. Okay, a lot of our resource definitions are written in plain text files and YAML files, which can be checked on to your source control if you're using Git and Git, whatever, and then introduced into your pipelines at various points when you want to deploy components to your cluster. And one of the other things that Kubernetes does pretty good is abstractions. All right, a lot of abstractions exist in the Kubernetes landscape because things are hard. Networking is hard, storage is hard, scheduling is hard, managing health is hard. There's a lot of challenges, as we saw before, and Kubernetes really tries to abstract away all of these difficult things to give us more easier time when we want to manage these production systems. All right, the idea of the reconciliation loop. This is actually a control loop, okay? The idea is you always want to compare between the reality and the desired state. You got your current state, you got your desired state, and you always strive to resolve the differences between those two states. Yeah, resolve the difference between two states, meaning you want to do a reconciliation, right? Now, if the desired state and the current state have no difference, then great, no one has to do any other job. But if there is a difference, that means that the controllers, the actual implementation of that control loop, has to take some action. Now, an action can be, let's create another resource. An action can be, let's delete another resource. Let's say I have several components running in my cluster. I want to do some scale out, and you have like 5 components at the moment. I want 10 components. Then the control will create another 5. If I'm doing scaling, then we'll just terminate the others, the unnecessary. All right. So the idea of a reconciliation loop is a really powerful concept because it abstracts away all that manual work we have to do. I don't have to do like Docker run, Docker run, Docker run, Docker run. I just want to tell Kubernetes, all right, give me 5 replicas of this. We'll just do it because it tries to, again, reconcile the desired state with the current state of the system. All right, let's talk a bit about the Kubernetes architecture. Give us some good background of how things actually work. All right, a lot of stuff because Kubernetes himself is built in a very distributed very distributed model all by itself, right? So let's try to break the things what we're doing. We have basically in a running cluster with multiple servers, we have 2 types of servers. We have master instances and we have worker instances, right? The master is like the green box over here and the workers are the blue boxes over here. Now the master naturally hosts all of the Kubernetes logic, the brain, the components that actually make the cluster tick and run. You got the API server, which basically is the entry point to the cluster. It receives requests from clients, from operators, let's say us. We want to create a new resource. We'll talk to the API server. And any other component in the system that also wants to affect or get data on the state of the cluster has to go through the API server itself. Now, the API server is API driven, obviously. It's based on an HTTP REST API, various API versions that support different kind of resources in the cluster. Next to the API server, we have the controller manager, which actually is the entity or the component that manages all the controllers we discussed a bit earlier. All the control loop logic, the implementation itself is defined as a controller. And the scheduler, which basically says, all right, you need 5 new containers, then this one goes to that machine, and this one goes to that machine, and that third one goes to that 4th machine, and so forth, right? He always looks at the list of what containers need to be run at the moment, and then just picks the relevant node, given it a list of constraints, and schedules that container to a specific node in the cluster, right? etcd is the state store for the cluster. All the cluster state is stored in etcd. The only component that can speak to the API server, to etcd, excuse me, is the API server, right? etcd is distributed by nature, it's consistent, it's a key value store, it's whatever it is you need from the states of the cluster. All right, so that's the master component. Over there to the worker components, we can say the kubelet is actually the daemon, the agent, the Kubernetes agent that runs on each of the machines. It receives the instruction from the API server, let's create a container, these are the specifications, great, and the kubelet receives that order or that information and then talks to the container runtime located on the machine to actually execute that container. It can be Docker, it can be Racket, it can be any other container runtime supported. There's also the kubeproxy, which naturally proxies requests. It's actually the entity or the component that does all the traffic relaying between various nodes inside the cluster, internal cluster traffic and external traffic to our users. And we have cAdvisor, which is a metric collection agent. Okay, collects various data and metrics from each node, how much CPU this node has, how much RAM, which containers are running, what's their health status, and stuff like that. All right. Over there we have our pods. We'll talk about them in a minute. And we have an overlay network usually deployed in the cluster just to make the, again, networking a bit easier than just using all the IP tables, heavy stuff we do on the Linux kernel. All right. Now, each of these is probably a topic for a unique session, each of these components, really figuring out and understanding how they tick and work. We don't have time to do that at the moment. Just, have like an overview, big picture of how stuff really works inside the cluster. Now, each of this is stateless, okay? All the state is stored in etcd, so basically I can say, well, I don't like how the scheduler works. I'm gonna write my own scheduler and just replace the default one with my custom one. That's perfectly fine. Those are loosely decoupled components. Sorry. Thank you. All right. So that's the Kubernetes architecture. Let's talk about a bit about the building blocks. Now, we mentioned pods, but let's talk about them a bit more, let's further the discussion about the pods themselves. Now, these are basically just really the basic building blocks in a Kubernetes cluster. Now, first of all, we have nodes, all right? You can think of node as a server, all right, as an EC2 instance or a virtual machine or whatever compute logical unit you want to call it. It could be even a bare metal server, okay? Basically, just compute resources and a container runtime we need to run our containers on them, right? We already mentioned controllers, okay? That's the implementation of the control loop, of the reconciliation loop. Over here, we have a bunch of other components which aren't really relevant for our discussion. The one that is relevant to our discussion is a pod, all right? Now, and this is a very important distinction when we're speaking about Kubernetes. Containers are not first-class citizens in Kubernetes, which means practically that we'll almost never manage containers directly. No, not almost, we'll never manage containers directly. There isn't even a resource called container inside the Kubernetes API. The smallest unit of work inside the Kubernetes cluster is the pod, all right? Now, a pod basically, you can think of it as a shell that, you can place containers in them. It's perfectly acceptable to run a pod with just a single container, but you can run a pod with more than a single container. You can have a single or 2 or 3 or 5 or 6 containers running in the pod. Now, a pod is a logical unit, which means that it's actually, you can think of it as the molecular unit inside Kubernetes. It moves around from nodes as a pod. All containers inside a pod move together. They scale together. They terminate together, all right? They're just the logical unit, the working unit inside a Kubernetes cluster. Now, the idea of a pod is that you can have, you can co-locate containers that have a lot of interaction together. For example, think of a web server that needs a cache, all right? So you want to keep them very, very close together because you don't want to pay for network latency. And you want to scale them together because each web server needs its own cache. So it makes perfect sense to co-locate those two containers together on the same machine and have the same address space and have the same capabilities and have the same storage possibly. All right, so that's exactly what a pod enables us to do. It allows us to run more than one container as the smallest working unit. Other building blocks you can see here on the slide. We have labels, all right? Labels are important. They're important when you want to query, okay? Give me a group of resources relevant to the front end. And then we'll just label all of those components with a key value, for example, tier front end, and then you can just query the API server, get all the resources labeled with the front end. Selector is exactly that query that we run. Think SQL, all right? Select this from this set of resources, all right? It's basically the same idea. And the service is a kind of an abstraction, which is kind of difficult to explain in like 5 minutes, but you can think of it as a load balancer, all right? A service will actually group a bunch of replicas of the same pods. Let's say I have my web server and a cache pod, and we have 5 replicas, and I want to route the traffic evenly to each of these 5 replicas. I would do that with a server, with the service, right? Which is designed exactly to do that. It's actually an abstraction above the kube proxy. The kube proxy is actually the one that does the routing, but the logical abstraction above the kube proxy is exactly the service, right? It uses labels and selectors to, again, bind to the group of pods that it manages and routes traffic to. All right. So just, to get a basic idea of what components or what resources we're dealing with, we're discussing a Kubernetes cluster. There are naturally a lot of other resources. We're not, not listed here on the slide, but this will give you a pretty basic understanding of how things work. All right. So now that we know how a cluster looks like, and now that we know which of the master components or the control plane components are in the game, and now that we have some, some basic understanding of what those components are and what the building blocks look like, what's a service, what's a pod, let's see how we can actually take all these ideas and, manage that application's health. So when is an application considered healthy? Well, basically, there are 2 types of concerns that we're looking into. First of all, it finished initializing. Let's say we installed a new application, we started a container, but it has to do some initialization until it can service requests, right? Let's say it's a Java application, for example, and needs to load a bunch of classes, it needs to create a database schema, it needs to have some, set of initialization steps that it has to do, but until he finished that initialization, he can't service traffic. So only when he finished it, it's in a ready state and he can serve traffic. So only then it's considered healthy. The other type of readiness or healthiness that we're looking into, that the process is actually running. It can actually respond to requests. It finished the initialization, it's running, everything is fine, but as long as it can keep serving requests, it's healthy. Now, a process might hang, or the process might crash, or some sub-process might be blocking the main thread, or there's a bunch of things that can happen. In all of these scenarios, the container itself might be still running, but the application inside that container can't service requests. And if it can't service requests, it's not healthy. The container itself, again, technically can be healthy and fine, and everything looks okay, but the process is hanging. So it's not there, right? It's not healthy, all right? So the kubelet, the agent that runs on those nodes, uses 2 probes to manage this, one for each state. There's the readiness probe and then the liveness probe. Now we'll define the readiness probe once the application finished its initialization and can receive requests. And we'll define it's a one-shot thing that happens, all right? Once it finished initializing, great, we're done. We don't need to check if it's ready because it's ready. The liveness probe, however, is something continuous. It's something that we want to check continuously through the life cycle of the application as long as it's running, just to make sure that it can actually serve requests. Now, if a liveness probe fails, that means the application isn't healthy, so we need to do something about it, or even better, have the system do something about it. If it's not healthy, great, just restart the container. All right? That combined with the controller idea that we discussed earlier gives us a truly system that can just fix itself. You monitor yourself, and if something fails, just fix it. I don't need to know about it, just fix it. There are three types of probing. You can run any arbitrary shell command inside the container. Any shell that returns an exit code of 0 means success. Anything else is not. Let's say you want to pgrep and for a specific PID. If you get a response, that's great. It means an exit code 0. If it's not there, the process failed or crashed. You get a different exit code, meaning the probe failed. You can run a simple HTTP GET on a specific URL if you have a web server that can respond to HTTP requests. Anything above or equals to 200, 203, 301, stuff like that is considered a success. Everything above 400, including, means failure, right? Or you can do just, try to open a socket, do a basic TCP connection. If you have managed to establish a connection, that means the probe succeeded and the application considered as healthy and can continue serving requests. All right, great. So I'll show you a quick demo of how we can configure and look at that liveness and readiness probe. So first of all, we'll look at the controller and how, if a failure in a pod, then the controller can step in and create another pod. And then we'll dig deeper and look at the container inside that pod and see how we can define those two probes. If one of them fails, then the container will be restarted. Now, the demo application, just a quick note about it. It was written by a guy named Kelsey Hightower, if anyone's ever heard of him. A great, really fantastic guy, as a dev advocate at Google Cloud. So I'm using this demo application with approval from Kelsey, but it's not mine, it's his. He wrote it for a book on Kubernetes, co-authored a book about Kubernetes. And it's a great demo application because it really, emphasizes the ideas that we discussed just now. So, we're jumping over to the terminal. Great. Let me just increase the font a bit so you see it in the back. Are you seeing it at the back? Great, perfect. All right. So I have a local cluster running in my computer. I'm using Minikube, which is basically a development tool used to exactly, play around with the idea of Kubernetes, API server, etcd schedule, stuff like that. But it's a single node. It's not like it's a single node cluster, which is weird. But yes, it's a single node. But it does help us to, test out new ideas and new configuration before moving them to a full-blown multi-node cluster. So I can use kubectl, that's the command line interface, for interacting with the API server. And let's try to list all our system pods and see who's up and running and who's not. I'll just, take the font up a bit. All right, great, perfect. All right, so we can see all our components, all our control plane components already up and running. We have the etcd, we have the add-on manager, which is an extension to Minikube itself. We have the API server, the control manager, the scheduler, all the core components used for running our pods, right? Let's take a look at what we have in the application workspace, namespace. Great, so we don't have a running pod at the moment, which is great because we haven't uploaded anything. So we'll jump over to the IDE. All right, so this is a resource definition or a manifest file for a Kubernetes resource. This is a deployment object or a deployment controller, actually. And you can think of a deployment controller. Get down. Thank you. And you can think of a deployment controller as a controller that's its only concern is to keep a specified number of replicas of a single pod. All right. So I define one pod per deployment object, and you just say, all right, give me like a couple of replicas of this, but the pod that we'll create will actually be according to the template defined at the bottom. Think of it as a cookie cutter. All right. You got your dough, and you got your star-shaped cookie cutter, and then just 1, 2, 3, 4, 5, and you get 5 star cookies. All right. It's the same idea. We define templates, and then we just let the controller create the pods from these templates. Now, the deployment object itself has some labels. This is the selector that actually binds the controller to the pods that we'll create. These are the labels for the pods themselves. And here comes the interesting part. All right. Great. Here comes the interesting part. We have one container in our pod. This will be the base image that we're running, the QRD and the 64. And the probes are defined exactly below. We have the liveness probe here, which will of type HTTP GET. All right, it will query the /healthy path at the URL or the IP address of the pod himself. There's a web server embedded inside this pod, so it can service HTTP requests. We have some delay, initial delay until the probing starts happening, because we want to give our pod or the container inside our pod, we want to give it some time to finish initializing and finish whatever needs to be done until it can service requests. The readiness probe, again, it looks a lot similar, but notice that this time it queries against a different path, right? The readiness queries on the ready path, and the liveness queries on the liveness path, on the healthy path, right? And this port and this container, this pod, also exposes an 8080 port, all right? So we can interact with it and see it in action, all right? So I'll just load this to my API server, and I'll just tell him to, let's apply from a file, and this is located in my Dropbox. Great. Deployment. Great. So our deployment was created. Let's say in action. We can see the pods themselves. This time, you'll note that we have a pod in the default namespaces, but it isn't ready yet. Okay, why isn't it ready yet? Because it hasn't passed a readiness check. All right. Now, if you'll remember, when we looked at the resource definition in the IDE, in the VS Code, we defined some initial delay seconds. All right, which means you have 5 seconds that the container inside the pod is running before it's considered ready, and only once it passes the readiness probe, it means that new requests will be routed to this pod. So let's run this query again. Great. So now it's in a ready state. All right. So I'm going to do a bit of magic here. I'm going to take this over to the side, and I'm going to open a new window over here. Great. So over on the left side window, I'm going to run that command again, but this time I'm going to run it with a wait flag. Sorry. Yeah. All right. So the wait flag actually tells us if there are any changes to the list of pods, it will print out a new line. All right. Now remember, this pod is baked by a deployment control, actually replica set control, which means if this pod crashes, we would expect that the deployment controller will start working, because there's a difference between the desired state, meaning one running pod, and the current state, meaning no running pods. So we'd expect that the deployment will create a new one. So over on the right one, the right terminal, I'm going to actually delete that pod. I'm going to run kubectl, delete pod. That's the pod name. Great. So we can see that the list over there on the left side, stuff begins to happening, all right? Our original pod, which was the HBJWM whatever, is now in a terminating state because we deleted it. But at the same time, we already have a new one starting, because the deployment controller notices that we have a difference between the desired state and the current state, and the desired state said 1, but the current state said 0, meaning I have to start a new container, a new pod, for example. So we have a new one called the 8W whatever, all right? So pods can crash, and it's fine. It's okay, because we have a controller listening, which can, create a new one if an application fails. Now let's jump over to the application itself and see the actual liveness and readiness probes in action. This is opened on my 3180. Great, this is a QRD, that's the web interface. I'm moving over to the liveness probe. All right, and you can see that this is being probed every 10 seconds, all right? So every 10 seconds, the Kubectl runs an HTTP GET command against the ready end path of the URL, and the QRD captures that command, it responds with a 200, and then prints it to the screen. So each ping, each probing actually returns a 200 state code. Now, I'm gonna take this one to the left, and I'm gonna take this one here. This is still on the waiting side, and I'm gonna fail the liveness tests, all right? I'm gonna tell him, all right, start failing the liveness tests, all right? And let's give it some time because the intervals between checks is 2 seconds. There, you see the status on the right corner? Currently, the application begins returning 500 error codes, not just 200 error codes. That's the first one, that's the second one, and the liveness probe will kill the container on the third one because that's what we defined in the YAML file. We said, all right, if you have 3 consecutive failures, then that means this container isn't healthy and just kill it, all right? Great. It's killed. Take a look over on the left side on the list of pods, all right? You can see 2 new lines. The one before the end just dropped to 0 because there are no ready state containers because it didn't respond to the liveness probe. So the kubelet killed it. But because it killed it, it already created a new one, and you can see that the restarts column, that's the one before the left one, jumped to 1 because we had a restart because the container was considered unhealthy, it was terminated, and a new one was created to replace it. All right? So using the idea behind the control loops, behind the reconciliation loops, and using probing, the liveness and readiness probe, we can actually let the system manage itself. We can actually let Kubernetes just tell him, all right, this is what I want to do, this is how we can check if things work, just make it happen, and just let stuff happen and fix itself if something bad happens. All right. Thank you very much. I'm open for questions if you have any, so now would be a good time for them.